Hello, we are back at it again with chemical kinetics. This time we are looking at the rate laws, but integrated rate laws, not the differential we saw previously with the method of initial rates. This is a new thing compared to your first year of kinetics, where you should have seen or saw a method of initial rates. Now we're getting to integrated. No, we're not doing calculus, we're not doing integration. If you want to see how the integration works on a rate law from a calculus perspective, in your reference packet for kinetics on my website, my buddy who's a math teacher wrote everything out and did some things. So if you're interested in the calculus of it, by all means, check that out at your leisure. So let's get into it. We saw this slide last time, except now we're going to focus on the bottom one, looking at the relationship between concentration and time. Notice with integrated rate laws, nothing in here has to do with the rate of the reaction. Differential rate law showed rate of reaction when dealing with concentration. Now we're going to see concentration and time. All right, so the integrated rate laws we're going to look at. We got a couple of them. Things to look at. So again, for reaction A going to products, the rate law depends on concentration. We're going to apply calculus to integrate the rate law. Gives us another equation showing the relationship of that versus time, which is the integrated rate law. So check that out, the document that shows how the integration works, and you'll see kind of more about what's going on. I believe your textbook may also show it, but I don't actually remember. All right, so integrated rate laws. Zero order, it's just looking at time versus concentration. If a graph of time versus concentration is linear, then we have this rate law. This rate law is not included on your equation sheet, so you should not have to do any math with it, but conceptually, zero order still has to be there. Notice the form of it, y equals mx plus b. So, a line based on it being linear. All right, first order. This is time versus the natural log of the concentration. If you graph time versus the natural log of concentration and it is a linear line, then you know that your reaction is going to be first order. So, zero and first order are basically the same thing, except taking the natural log of both sides. Again, this equation is on your equation sheet, but I'd suggest writing it down because we are going to use it here today. And then we have second order. Time versus 1 over the concentration is linear. So if I were to graph time versus 1 over the concentration and it produced a linear line, then I end up getting this lovely equation. Again, still in the form of y equals mx plus b. Any questions? All right, half-life. Half-life plays a big role. This is not the same half-life as in radioactive decay. Mathematically, we're going to show that now. But radioactive decay cannot be influenced. Half-life of carbon-14 never changes under any condition. Half-life of reactions, depending on the type of reaction it is, can be affected. So what I want you to do, how would I represent half of an initial concentration disappearing? Hopefully think of it this, at some other time, half the initial concentration. So what I'd like you to do on your paper is plug this in to my zero order rate law, and I'd like you to rearrange and solve for t. Take a moment and do that now. Okay, welcome back. Should have gotten this. So the half-life of a zero order reaction is the concentration, depends on concentration and 2 times rate constant. All right, first order. Again, let's take the above initial concentration over 2, plug that in to this first order equation, and again, rearrange and solve for t. Please do that now on your paper. All right, you should have gotten this. Now, notice something here. Half-life of a first order reaction is the natural log of 2 over the rate constant. There is no concentration relationship, and that's a big point. First order kinetics follows true half-life the closest. Does not follow it perfectly, but it follows it the closest because there's no dependency on how much you have. All right, second order. Again, please do the same thing. Take your 1/2 of initial concentration, substitute it into this reaction, and solve for the half-life. Do that now on your paper. Okay, here we are. Should have gotten this. Notice concentration is in this half-life equation. So 0 order and second order have a concentration dependency, whereas first order does not have a concentration dependency. That's kind of the big kicker. I believe the first order half-life equation is on the equation sheet. The other ones are not, but you hopefully have shown yourself today that you can plug it in and derive it yourself anyway. So it makes life easy in that sense. All right, so relationships. Again, 0 order reaction, the lower the initial concentration of the reactant, the shorter the half-life. So since it's a direct relationship, conceptually, we can figure out what's going to happen to half-life as you change that concentration. That is something you may have to do on the AP exam. Again, no math, but just conceptually explain what's going on. For first order, half-life is independent of concentration. There is no concentration relationship. As I said earlier, it's the closest to true half-life. Natural log of 2 over k, which is just 0.693, as you saw previously. Second order, it's inversely proportional to the initial concentration. So if I increase initial concentration, half-life becomes smaller. You understand an inverse relationship. But again, you should be able to discuss this conceptually on any question. Mathematically, first order half-life you may have to do, but conceptually 0 and second. All right, so our whole goal with integrated rate laws is a lot of graphs. And you're going to be looking at graphs. You're going to be analyzing graphs. You're going to be taking portions of graphs in order to figure out what's going on. So if you notice so far, we only have one reactant. Integrated rate laws only works with a single reactant. You cannot do integrated rate laws as they're supposed to be used or completed with more than one reactant. So notice here it says A going to some product. So what you need to do is you have to plot all 3 possible rate laws. Plot A, concentration versus time, natural log of concentration versus time, and plot 1 over concentration versus time. The goal here is when you look at all 3 graphs, which one gives you a straight line? That's all you're looking for. College Board may give you the 3 graphs and you pick one. College Board may have you plot data, graph it yourself, and then pick one. Either way, you're looking for whichever one is the straightest line. And trust me, it's going to be blatantly obvious which one is going to be linear and the other 2 are not at all. Ultimately, when you figure out that which one has a linear curve, you automatically know the order. Because if concentration versus time is linear, there's your rate law. If the natural log of concentration versus time is linear, you know it's first order. And if 1 over the concentration versus time is linear, it's second order. So what you need to realize is, graphically, once you've determined which one is linear, you automatically know the rate law. And you automatically know the integrated rate law. College Board is not going to tell you these things. You need to figure out, like, oh, I know graphically it's this, therefore my rate laws that I can use to solve the math part of it, I know from differential, which is shown on this slide, but then I also know integrated because I know the order. 0, 1, and 2 are the 3 main ones you're going to come across in the course, but please realize that orders can actually be decimal places, orders can be fractions, orders can be negative, orders can be anything they need to be or that you get from experimentally determining it. So when you get to college, it's not just these 3. It's infinite numbers of orders. So for example, let's say we graphed concentration versus time. That's the blue line. Okay. And now we graph natural log of concentration versus time. Again, the blue line. And then we graph 1 over the concentration versus time. And then the blue line. So again, here's concentration. Here's natural log. Here's 1 over. Of those 3, which one should the answer be? It should be 1 over concentration. Therefore, for this made-up data, the reaction is going to be what order? Second order. All right, so let's solve a problem. Here's some data. Don't copy the data. You're not going to do this. I'm going to show you everything. We want to figure out what the integrated rate law is. We also want to find out what the value of the rate constant is. So many ways to do that. If you took statistics, I am actually dumber because of statistics in college. It was not fun for me. But if you know linear regression and all that stuff, by all means, go ahead. So concentration versus time, there's the graph. Regression analysis, obviously we're looking at our R squared value. The closer to 1 tells you how linear the line is going to be. Next, let's do natural log of concentration versus time. Here's our graph, regression analysis, R squared, 0.99978. So yeah. And then 1 over the concentration, graph that one. There's our regression analysis, R squared value. College Board is not going to ask for the R squared value, so don't worry about it. It's more for you, if you know how to get it, just to kind of back up your answer. So we know the winner is time versus the natural log of concentration. Therefore, I know it's first order. Just because graphically the linear line was based on those 2 things, I know it's first order. Therefore, I know the differential rate law. It has to be this. And therefore, I know the integrated rate law. It has to be this. So graphically tells you number 1. Number 2 and number 3, you have to automatically realize you have that information. But wait, what is the rate constant? I need that number. Well, obviously it's in the form of the integrated rate law, y equals mx plus b. So I can solve using the slope of the line. So there's my data. I can pick 2 points. And I get my slope. We always got to remember the rate constant is negative slope. So again, rate constants are going to be positive anyway. One thing to note here. The slope of the line is not the rate constant. You get the rate constant from the slope. I bring this up because in the past, there were some questions on the AP exam where it asked, where do you get the rate constant from? Having to do with integrated rate laws. And a lot of students said the rate constant equals the slope or the negative slope. College Board did not give credit. The students had to say the rate constant was determined from the slope, not is the slope, but from the slope. It seems like semantics, I get it, but it's happened in the past. I don't want you to get dinged in the future. Method 2, again, if you know your regression analysis, same idea. It's your A constant. Again, don't have to do it this way. Method 1 is going to be most likely what you're going to do in the end of the day to solve for it. All right, so again, first order integrated rate law is natural log versus time. Slope is negative k. For second order, 1 over the concentration versus time. Notice now slope is positive. So first order, it's a negative slope, but second order, it's a positive slope. So got to keep that in mind when you're doing things and how you're solving these problems. This graph or picture is in the reference sheets. I do suggest printing it out, probably 50% size, maybe 80% size, all depends on how much room you got, and put it into your notes. It kind of sums everything up in one page altogether, which is going to be very helpful in the long run for you. So please keep that in mind. Now, what happens if you have an integrated rate law, or you want to do an integrated rate law, but you have more than one reactant? And as we said earlier, the integrated rate laws only work with one reactant. So we have to basically create the condition where only one reactant has the control or the influence of the rate. So let's say we have this reaction of A, B, and C going to something. Now the goal here is one reactant has an extremely low concentration and the others are much higher. When College Board sets this up for you to hopefully have the realization, it is blatantly obvious to the effect that, let's say we're focusing on concentration of A. A's concentration is going to be some decimal number concentration, 0.039, 0.025, like something very small. Where B and C, its concentration is going to be on the order of like 5 molar, 8 molar, something astronomically larger compared to the one you're focusing on. So if we assume and we make the condition that B is greater than A and C is greater than A, then during the process of the reaction, B and C don't really change that much. A is going to have a profoundly big change, but B and C are so big comparatively, they don't affect anything. So I can rewrite my differential rate law as K prime, that's a little apostrophe, times the concentration of A raised to the n exponent. The prime just means the rate constant under some other condition. And the other condition is the concentration of B and C are so much larger than A, they don't affect the rate or they don't change, but A does. We call this a pseudo first order rate law, or a pseudo zero order, or a pseudo second order reaction or rate law. The simplification, it just yields a rate law of a particular order. So whatever A actually is, 0, 1, or 2. And again, the prime means pseudo, so it's some other condition. It's not exactly the same as the initial rate law on the top of the page, but it's something different. Any questions on this? All right, thank you very much.